сюда обратно.
Dark or grip, bet studentam jāzina kaut teorētiski, ka ir tāda distance aizsardzība.
Distance aizsardzība.
How are you? Fine? What about your RC?
I got it.
Got it? Oh. What would be? May only class grade.
Yes. Actually finished.
Actually finished? Or diagnosis?
Так, привет. О, ну что? Time is running. Okay. Let's start. Yeah, let's start. Can we start?
Yeah.
Okay, let's imagine we are in New York 100 years ago and we have a power plant. 4 nice machines. Bus, circuit breaker. Goes to city, not very important. So power plant 4 machines works to city network. Very good. Where's the problem? Daytime. All machines are working. But at night, not enough customers. No one to sell energy. So, at night time, only one remains operational. So what? So that. For night time, we have what? Fold. It's for night time. What we have for day? For daytime, we will have the same AQ, but we will see only 1/4 of resistance. You understand what it means? What fault current changes twice a day at last. This means what we need to change protection settings at last twice a day, all over the network. It's a blueprint for disaster. First, it's labor, but the key problem, sooner or later, someone will not change it properly. It's a complete mess. What's the first idea? We need something what can change the settings automatically, without necessity for someone to go there, open the door, I don't know, put some key in and switch, day or night. This should happen, what on the free machines are operational. We need something adaptable. We need protection, kind of protection, being able to adapt to regime change. Once more. AMF changes a little. This part is how to say power plant equivalent reactance. This one is variable. Then some kind of line resistance fault. Here is current available to our relay. Yeah? But what if we take this voltage? What will happen with this voltage if number of operational machines increases during fault time? If, for example, we have now draw for one machine, let's say we have 2 generators. What will happen with this voltage? Decrease or increases? This resistance will be 1/2, yes? So voltage will be high. Yeah? Yeah. Meaning what we need, what to do with relay setting, protection setting? Increase or decrease? Current. Increase. We need something what can do like our trip current being some kind of one against this relay voltage, yeah? So maybe some kind of function Is it correct? The higher voltage or proportional will be the higher voltage, the higher should be current, yeah? So, maybe like this. Okay. This one, yeah, this one is correct. Huh. What can we do? The first idea, correct me if I'm wrong, but it was Westinghouse. Idea is to use device called balance relay. Idea is to take current balance. Here is a core. Coil with current. Is it nice? Can I draw better? Coil with current. The higher current, the higher will be drag force this way, yeah? And if this distance is Li, here will be moment Li, Fi. Proportional to what? To current. The higher current, the higher is drag. So here can be do it in red. Actually, it should be silver. Okay, it's red. So it's a contact. If they close, trip signal, disconnect signal will be sent. On the other side, another core. At this moment, this is simple over current relay, isn't it? It's simple relay operating in E3. Idea was to add a second coil. Voltage. Here we will have voltage, moment of voltage. Attempting to, what to do? I need to, some kind of limiter here. What's going on? The higher voltage, the higher is kind of, if this one is go moment, to 3. So this one is, let's say, go, and this no go or breaking moment. It operates against 3. It's how to stay back dragging our relay. I can select with this switch. It's a current plug. I can select factor for this moment. When this relay is tripped, it trips when current moment is greater than the voltage. Yeah? It turns left and close contacts. taking into account radius, factor, force from voltage, of course all the solenoids designs. Finally, we will get something like this. Current divided by voltage should be greater than K and some kind of relay constant. This factor and some kind of, actually it's y0, it's a constant of our relay, it's simple design of it contains number of turns in these coils, its magnetic properties and blah blah blah. So it's simple design constant. It can be changed when the relay is created. What do we see in reality? Current divided by voltage greater than some kind of trip constant. What is current divided by voltage? Conductivity. In closer look, this relay is not a simple current relay. Simple current relays simple current relay is current greater than some kind of trip merger. Here we go to conductivity is greater than kind of trip conductivity. So this type of self-adjusting relay, it's a self-adjusting relay, yeah? This kind of self-adjusting relay is in deep maximum conductivity relays. It is not no one likes to analyze conductivity because you have trip areas outside of something. Much easier to go from conductivity to what? Resistance. So this relay will be actually a relay of minimal resistance. This relay is trip if observed resistance. If you divide voltage by current, it's resistance in ohms. So this will be minimal ohms relays. I can write what it's a min ohm relays. This group of relays acts as a minimum resistance relay. We are dealing with AC circuit, yeah? Yeah, and when we look at AC circuit, it can be active resistance and reactive resistance, yeah? Coil, there is a coil somewhere. Capacitor there. To perform analysis on resistance relays, we need a tool. This tool called complex resistance plane. It's a chart in coordinates R, active resistance. Jx, reactive resistance. Positive reactance is coil, negative capacitance. Such kind of chart is used to analyze performance of such relays. Okay, let's try to understand where we are, what can and what can be done. Let's assume we have system 1, line 1, here line 2, here will be line 2, and it goes to the system number 2. And let's say we are here. We are here. Force R, force X. Oh, here is my resistance chart. And let's say we have, here would be nice red fold number 1. Let's say it's three-phase fold at the end of the line. What will see my relay? Here we are. We stand here. Here is our voltage. This way will go our current. What will see my relay? Of the first systems, resistance of the first line, resistance of the second line, and here is voltage for my relay. Ground, and this is current for my relay. Is it correct? I have three-phase fault, so I can ignore everything from the left of my fault place. Is it correct? Here, what see my relays? My relay. Okay, but so it can be 3 relay each for each phase. I will see full resistance of second line. Should be approximately 70 degrees. Point number 1. Distance from the 0 will be resistance of the second line. For I'm assuming overhead line. For overhead line, angle is approximately 70 degrees. Point 1 is clear? Okay, let's take point 2. Point 2 fault at 0 distance. What will see my relay? Voltage will be 0 and calculated resistance will be 0. So point 2 goes here to the 0 point. All other faults along second line will be located somewhere here. Yeah? Okay. Now let's take fault 3. At the 0 distance, 0 mile or 0 kilometer of the first line. What will we see? Current from the opposite system. And voltage drop on first line. Yeah? So what should it be? Resistance of the first line. Yes? Agree?
Yeah.
But current flows from opposite side. And if current flows from opposite side, what does this mean? Approx 70 degrees. This means what we will see, this resistance, but not normal resistance of line is approximately 0.4 plus 0.2 plus 0.4 ohms per 1 kilometer. We will see the same angle but in opposite direction with the minus sign. We will see it as negative active, negative reactive. At the distance of 1. And to make this complete, I can take this as number 4, and number 4 will be somewhere here. Here is picture for possible faults, internal and external. These are internal, these are external. So, what can we say? Internal faults are in quadrant number 1. This is area for internal faults, and external appears to be located in quadrant 3. Okay. Is it clear? Now, if I have relay, with characteristic like this, simple balance relay, how will it appear on complex plane? As a circle with radius again internal faults, external faults. What can you say about characteristic? Is it okay? protection trips if observed resistance is inside this circle. Possible points 1, in blue 2, orange 4, and possible yellow 3. Your opinion? No. There is no. This will not work. Such simple balance relay works only on radial lines, on lines power from single end. For double fed lines, this will not go anywhere. No? What should we do? Where should we run? Any idea? What means dots? Directed overcurrent relaying. Yeah? What was instrument in directed overcurrent relaying or measure to make protection directed? Power direction relay. Yeah? Yeah. So first idea is to do like this. Voltage goes to K means relay, that means resistance. Relay of minimal resistance. And simultaneously K relays V watt power direction relay. Current A. Current. And they are combined width and block. So only if we have one binary one from a resistance relay and from power direction relay, protection may operate. approximately minus 45 degrees. Here is operation characteristic for power direction relay from directed overcurrent protection. Are you familiar with directed overcurrent protection? It's our protection number 2. First was simple overcurrent and second directed overcurrent. This one, this line with its normal vector at minus 45 degrees is from directed overcurrent protection. Blue line is from distance relay. Why it's distance? Because resistance of fault is, if this is alpha, will be that of 1 kilometer or 1 meter multiplied by alpha by distance. Distance relay. Here I can draw it in yellow. This is effective characteristic of combination minimal impedance or minimal resistance relay plus power direction relay. This thing will not operate on external faults. Much better. This is first, I'll say, first version of real operatable distance protection. But it's only first approach. That's a problem. That's a problem. First, I can draw it. Maybe better. It's a, how to say, generation 1. That's a problem with generation 1. Problem with generation 1, if you have fault with transient resistance. It's a resistance of arc or 3 or what felt on your line. You have fault with transient resistance. Let's say it's at a distance of alpha. Okay, something like this. Your operational characteristic. Approximately 70 degrees, it's an angle of your line resistance. Let's say it's somewhere here. alpha. So this point is alpha. Line resistance till a fault place. Yeah? Yeah. What I need to add pulse transient resistance. You see what happens? Without arc, if there would be no arc, if it would be metallic fault, everything is okay. My protection operates safely. But if I consider fault with transient resistance, I'm in trouble. At the end of the line, because of the slope, my relay will not operate correctly. It will miss internal fault. So generation 1 wasn't really reliable when we consider faults with transients. Here, in our area, many faults are caused by falling trees. Falling tree is a transient resistor. It will not burn through instantly. This means what generation 1 isn't reliable. Here. Somewhere, protection of generation 1 worked well. Really. It depends on probability of transient resistance. Generation 2 was smarter. For generation 2, this kind of characteristic were implemented. Shifted circle or ellipse. Something like this can be used. Why? Because of load regimes. When we see power transfer from system 1 to system 2, this is possible area where we can see real resistance. It's because of power transfer from system 1 to system 2. In opposite direction, it's a closest area. Actually, some scholars prefer to draw it from this point. It's a huge area. This kind is clear. You can analyze. So in case of high load, this gap is insufficient. That's why, so in case of high load, can be something like this. So in this one is both active and reactive power transferred to this system. This part, active, goes this way and reactive from system 2. In case like this, to prevent false operation, elliptic characteristic was preferable. It's a generation 2. Here. This one is a generation 2. generation 2 relay. But then again we see not the best for case of high transient resistance. For generation 3, base idea was in for generation 3, base idea drawn from a minimum reactance relay. From relay operating on minimum reactive resistance. Characteristic of such relay will be like this horizontal line. It's pure theoretical. You cannot realize minimum reactance relay because of what in opposite. Because of what regimes. So you need to create borders. Actually, this one is your line angle. It's common today to draw this border of characteristic with the idea to ensure safety margin between maximum load point and your characteristic. Also, these two margins are needed. I will explain why. They are drawn this way, not zero. In theory, this line should be. In theory, this line should be. X equals to 0, and this line R equals to 0, but they need some slope. I will explain why. This kind of X characteristic is a generation 3, today industrial standard. Now attempts are made to create generation 4, most adaptive. Generation 4 may look like something this way, but it's not practical because of high computation burden. So this, at a present time, Gen 4 characteristic is somewhere. It's in scientific works, but not implemented yet. Okay. Now let's try to understand how protection schemes are created, how protections are coordinated. What we need to get, we need sensitive and selective, yes? Should be able to distinguish internals from external, selective, and operate on any internal fault means sensitive. Yeah? Yeah. So we need to create some kind of schematics, somehow to coordinate our protection. A1, A, B, Y1. Simple network. In the middle, here should be some client. Let's omit. What do I need to draw? First ID. I need a safety margin. I will create some kind of protected zone. In go, no go. I need safety margin between them. Yeah? My relay may be imprecise, my transformer may have error. It's normal. I have current transformers with error 10%. Let's say I have typical 10p. I have better. Happy days. I have voltage transformers, 10% predictable error. That means what my safety factor, in Latvian drošums, safety, should be 20%. Yeah? Yeah. Because this is minimum, not maximum current, but minimum resistance relay. Remember this digit, 0, 8. 80% off. It will left 20% margin. Now let's go. Zones are created in the overcurrent protection style. A1, C1. Instant time for A1 will be 0, actually not 0. I need to set some 50 milliseconds. C1 again, nearly 0. But what will be trip relay? How did we select it? Operation margin for the first zone of overcurrent protection, for instant zone. With the 10% safety gap from the end fault, yeah? So here, at the end of line, is a fault place. I should guarantee what here is a safety gap between end of the A and begin point of the C. This means what? A1 is 0A of first line resistance. Complex. Is 0A. Is it clear? Yeah, you understand what? Next one. I will have A2 and A3. time here will be 1 delta t. 1 delta, half a second roughly. Here, selectivity in the same way we did it with overcurrent protection. They are selective because they have safety spread or safety area in time. So, R2 is 1 delta t, A3 is fine, but where? What's important? This gap. I need 20% gap between end of second zone of A2 and beginning of second zone of C2. This point corresponds to the operation of C1, yes? Or 0.8 of second line resistance. Important moment. A2 will be 0.8 resistance of the first line plus 0.8 resistance of the second line. For the third zone, it will be something inside system 3, or at last, for the last zone, load resistance is the bottom line. So, or maximum transfer capacity. But in reality, you will see next line or transformer. This zone will end here. You will have connection transformer. So it will end inside this transformer. In opposite direction, you will see D1, B1, B2, B2, and this one, D3. This is what you will see, you will design. Same technique, not the same, but derived from directed over current protection. Here is everything very simple. What's not so simple? This is not so simple. One moment, I will draw complex plane. I will try to create chart for complex plane. One second. Create a chart. Active resistance, inductive resistance. Approximately 7 degrees, bit shorter. This is angle for fuel and resistance of the first one. Fine. What do we know? A1 should be 0.8. Correct? Correct, because I assume error of 20%. Here is this point. I can draw one moment. This is point corresponding to this formula, but nothing prevents me from extending active I can go equals 0.8. Why I'm doing this? Because what limits me on active dimension? I wrote this first. This gives me this point. But what limits me on active direction? This area of transfer, power transfer from system 1 to system 2. I can extend active margin of first zone till I reach 20% safety distance from the load. Why I need to extend it? Because I can face fault with transient resistance. The far is better than close because of transients. Great. This is my A1. This is 0.8 point, I can mark it. Now, tell me, where on this chart is a 0 point or reference point for protection C? Where this bus is? Here, at the end of the first one. Blue is coordinate system for protection C. For this protection, have you heard about Einstein's relativity theory? Relativity theory.
Relativity.
Yeah, relativity.
Newton's.
Not Newton's, but Einstein's.
Sorry.
Einstein, bit in German. Here you have example of this common relativity theory. Better go ahead. if you, it's not for everyone. And here is example of relativity. For the protection A, this point is located in coordinates L1, X, Y1. Yeah? For the protection C, this point is located at coordinates 0, 0. Reference point or 0 point for A is here, for C it's here. So blue lines are protection C. And this one is a resistance of second line. At approximately 80%, maybe a bit longer, like this. This is C1. In blue, I draw C1. Zero 8 of the second line. Now, where the 3 point for the second zone of A, for A2. Should be 0, 8, first line plus 0, 8, second line. So this leads me to 0, 6, V2. Yeah? A2. 0, 6 point. So what do you see? Somewhere this way goes C2 also. A3 not important. Important. What do you see? A2 overlaps with C1. Yes? Yes. In this area, A2, second zone of the protection A, will operate as a backup for the C1. They are selected because I, spreaded them in time. Yes? Yes. And I got, what? I got safety. I have increased safety because in case C1 fails, A2 will operate. Fine. One moment. One moment is what moment? Moment of moment of last zone coordinated with word. You can read many books on distance protection, and all these books will suggest you to select trip conditions for the last zone as something like 0.8 of minimal load resistance. all these books are written in the times of generation 1 or generation 2 characteristics. In case of Gen 1, Gen 2, you are limited in the shape of your characteristic. So you cannot freely select your shape and slope of your characteristic. Now we are in generation 3, maybe even generation 3 plus. In case of generation 3, first versions of Gen 3 had a limitation on ratio between L and X. Some have 7, some 10, so not absolutely free. On modern relays you can extend active part far from 20 of reactive. First. Second, sometimes you face problem. This line is too close to load. Modern relays offer you cut off in characteristics. So for modern relays, you can have cut off like this for your power transfer regime. You can have cut-offs. So you are not so bound on this active border. Meaning what? Meaning what you said for the last zone, you can quite freely select your trip conditions. Okay. Now. I would like to have deformations on the second part, but for this one, yeah, first moment, input values. Before I draw some voltage and some current, relay operation signal. Very nice. But what should I connect to my relay to get relay resistance being division of relay voltage to relay current alpha that way? I need relay to measure fault resistance. And there is first moment. Modern distance protection, all distance protection, real existing, do have absolutely separate processing trains or processing flows for line-to-line faults and for line-to-ground faults. Absolutely separate. For line-to-line faults, it's simpler. Actually, many old sets didn't have line-to-ground part, it was substituted by Earth's fault protection. Earth's fault protection is cheaper and really it's a bit more reliable. So many old sets had only line-to-line faults, this how to say procession flow or this processing part. For this part, quite simple idea was used. This relay was set, for example, UA EA minus EB and so on. They were sitting on line voltages and current difference. This Gen 2 relay has two current inputs. And inside it calculates difference between. It sets on line voltage and current difference inside is a current 1 minus current 2 operation performed. This ensures what in case of line-to-line fault, line to line, everything will be fine. Line voltage, difference of phase current. More complex thing is with the Earth's fault relays. Earth's fault relay, if we took, okay, I have source, I have N. Here is my line, here is my fault, and current returns where? In ground, yeah? Current returns to the ground, through the ground. To get fault resistance of the, I need to exclude ground part from the overall measured impedance. Yeah? Yeah. So, in this area, alpha z direct sequence ground, this is M1, this point M1, M2, M2. This is again alpha Z1 direct sequence, because direct and negative sequence are assumed equal. Alpha Z1 is in zero sequence, M0. Here flows A of direct sequence. Here is the model assumed. It's very basic model, but it is how it is. In this model, in this model, so assuming this is phase voltage. sequence A negative EA 0, we need to exclude from the overall fault resistance this part, voltage drop on this part. Yeah? This one needs to be excluded to eliminate Earth's influence. So, to do it, idea of compensated phase current used. So, that is calculated by phase voltage divided by phase current plus 0. This one is zero resistance and is directed by direct sequence. Compensated phase current. All the relays used, it's a real, actually it's a complex. So, to eliminate zero sequence impedance from the overall resistance, compensated current is used, this part. Some have triple here and triple zero sequence current. Moment. Zero voltage drop from zero sequence is eliminated by introduction of compensation factor. I hope I'm right. Wait a second. Trust no one. They were historically, where attempts were made to create relays for all three phases. They used compensated voltages and currents and had operational characteristic like star on all three phases, but ended with nothing. It was a dead. It was useless. It was waste of of time. Where is my overall line resistance or resistance per unit, per 1 mile and per 1 kilometer. Okay, I think we can end part 1, and in half an hour we will start part 2, where we will discuss problem. I have a name for it, zone deformation. So, I think we can continue